to Chris, because I've known Chris for many years as a very well-established researcher, but I think also as a friend of mentor to many of the researchers in the Design Society. Chris, I think, is somebody who really touched with his research and with his personal interaction the life of many of the younger researchers in the design community. And so it's very nice to see an overview of what he has been doing. So over to you, Chris.
Thank you very much indeed, Claudia. Thank you for the introduction, and I look forward to the discussion this afternoon. I'm just going to share my screen if I may, so this may take a second. So the title of what I'm going to talk about this afternoon, studying support for design and designers, but really the subtitle is the more important thing, a lifetime searching different things, a lifetime searching myself, but a lifetime interested in search and how we search and how we support it. So a little bit of a pun there. The overview that I gave you was that it's going to be reflections on professional life working in and studying design, and it's in four parts really. First of all, I'm going to talk about my early years as an academic and really the struggles in those early years, which I hope maybe will give some solace to others who may be struggling in early years of work. My first years were very difficult. I want to reflect that a little bit, searching for a research niche, then talk about a middle period, which I think was quite productive, but in particular because I had some great people to work with. And I'm going to talk a little bit about those. And then the third part is working with the wider design community through the Design Society and also through involvement in ISED. And I hope that may stimulate some discussion in particular there. But a little bit of background. I've been enormously privileged to work in three great universities in three great cities. University of Bristol, which is my hometown and top right. University of Bath, which is nearby and where my father worked. On the left here, the beautiful Georgian city of Bath, and most recently the Technical University of Denmark, just north of the lovely city of Copenhagen. And to any interested in great places to work, I would recommend all of those places to you. But how did I get into this? I think probably the turning point for me and a lot of those my age in Britain was a report that was done into the engineering profession at the end of the 70s called the Finniston Report, Engineering Our Future. And that recommended a shake-up of engineering education in Britain, introduction to 4-year master's courses. It also built on another report which the Design Council had done a few years before, headed by Alex Moulton, which suggested that design should be a thread running through all stages of professional formation. And the consequence of that was a lot of British universities recruited people in the 80s to teach design. And we together had to try to work out what that might mean in terms of research and teaching. But it was also very important time for other reasons. It was a time of political change. The difficult 70s were followed by the difficult 80s in some respects, but Margaret Thatcher, Ronald Reagan, globalization in Britain, a big decline in industry, but also other important threads. I said starting in 81 in Rome. I didn't learn about it for a few years, but the IBM massive in the world, all of those were important influences. But before I go on to that, a little step back. I studied engineering at Bristol. I graduated with a bachelor degree, and then I went to work in the railway industry, in factories building railway carriages. I worked on the train on the bottom right. The French have the joke that the British developed the first train. Unfortunately, they're still using it. And I think that does apply to some extent. But at the beginning of the 80s, I joined a company called Ricardo Consulting Engineers, consulting in mainly diesel and petrol engine, internal combustion engine. I was the personal assistant to the director of design. And we were working on all over the world, designing and developing engines for people, including top right is a picture of an engine we designed for China at that time that's still being built today. When I went into the design office, it was drawing boards, but after I'd been in about a year, my boss had a heart attack and they had to find other work for me to do, and I got involved in the company's computer-aided design system, the McDonnell Douglas automation system in the center here. And I got involved then, as well as administering the system, in writing parametric programs. I wrote programs for all sorts of, engine parts, standard gears, fasteners, and so on, programs to draw the combustion chamber that we worked on. But I also helped the staff that were working on trying to output our sort of standard drawings. This is a typical example of a cylinder head drawing we were producing at that time. I learned a great deal. I spent 3 years working in CAD at Ricardo. I had a choice. Do I stay in engines? I chose to stay in computing. I was invited to join the University of Bristol, which I joined in '84. But in those 3 years, I learned a great deal, I think. First of all, the importance of serendipity. Serendipity is something that's applied throughout my working life. By chance, my boss was ill. They had to find something else. I was put onto computer-aided design. I had no particular interest in computing, but that's a lifetime interest. But while I was there, we had a text-oriented database. We were a consulting engineering company, and information was a sort of lifeblood to us as consultants. And the computer system I used most was the text-oriented database, searching for through the company's records and our index of other documents. I also at that time learned to be very wary of the hype about new technologies. At that time, the CAD vendors were saying we'd get a 300% improvement in our productivity in our drawing office. Well, we got nothing like that. And in some respects, we had a decline in productivity. And we spent a great deal of time and effort producing tools for people to use in the context of CAD, and they weren't used very extensively at all. Learned there about the importance of application context. We needed to understand the application context of new tools if they were to work properly. And you almost needed to redesign the process as well as redesigning the tools. Much later, I also realized at that time I made the choice to stay in computing because I thought engines are an old technology. There isn't much development they can do. I was young and innocent then, and it proved to be the most exciting 20 years in the history of the diesel engine, perhaps since then. But I joined the University of Bristol in the mid-80s, and I want to illustrate the dilemma I found myself in with this picture. This is from colleagues based on a description of design from Christian Weber, Moens Andres, and so on. But in design, we as designers model the characteristics of the designed artifact in order to achieve some life cycle properties. And we use analysis tools based on use cases and methods and standards and codes in order to evaluate the life cycle properties from the product model, from the characteristics. And we use synthesis based on methods, components, elements, experience, and so on, in order to generate the characteristics to achieve the properties. And the whole of that we document. And if I look at in the mid-80s, when I joined the university, feature-based solid modeling was present. We were just about to have parametric associative models. So the 87, I think, was computer integrated manufacturing was well established. Standards, IGES, PDES, set solid and so on, working towards the development of the IGES standard was out. There was work on design catalogues, Ashby's material selection charts. People were trying expert systems. Design for manufacture and assembly was established. I think was 86.7, something like that. Quality function deployment was in use. Finite element analysis and computational fluid dynamics were all well established. Multi-body analysis beginning to get established. There was standards for logistics support. There was the protocol wars between the ISO, Open System Integration Standards, and Internet. Office software was coming on. MRP, MRP2 were coming on. Text databases, hypertext, all active areas. And of course, computer supported collaborative work was also becoming active in the 80s. And to some extent, I was like a child in a sweet shop. I didn't have a PhD. What should or could I do? And for 2 or 3 years, I completely struggled to get any sort of research established. Instead, I spent my time working with the Apollo workstations that we'd adopted for CAD. And in fact, what I did then led to a book on CAD CAM. I spent my time reading and studying. What actually gave me a research direction was pure serendipity. At that time, there was a man called Malcolm Sabin, and he had written the British Aircraft Corporation numerical master geometry system, and he advised the EPSRC, our funders, on research in CAD. And a colleague from Bristol, who I didn't know at that time, had applied to the EPSRC for funding for work with a local company on a computer advice system for design and manufacturing specialists. And Malcolm Sabin came to find me at Bristol and said, think you and John would get on well together. I'd like you to work with him on this project. And I joined in with that. And then shortly after, my head of department, who was a fatigue specialist, put me in touch with fatigue specialists at Rover, at the Rover Group, Rover Car Company. And John and I together put a proposal for a knowledge-based advisory system for design and development of automotive parts. I didn't know what I was doing in that area, but John was interested in expert systems. His colleagues in engineering mathematics were interested in uncertainty. And this was an opportunity to learn together. And so really that got me started in research. We looked at all manner of things. The company that we were working with had tried to work on parametric design automation and failed. And we tried to understand why that was. And it was because all the parametric programs they'd written could only be used when you had complete data. And in the early stages of design, they only had imprecise and incomplete data. Therefore, they weren't able to use these parametric automation systems. We started looking at other things. We worked with Jamie Shah at Arizona State looking at features. We started looking at the importance of what we'd see today as application managers, execution engines in computer-aided design. These systems which pass data from one program to another for example, for Monte Carlo search or for optimization. We built our own system in the early 90s based around Petri nets as the means of controlling the application engine. But also in that work, we came to meet up with other people with similar interests. In the early 90s, the universities of Bristol and Bath applied for an engineering design centre. There were a number funded in Britain at that time. The Cambridge EDC was one. We failed to get any support, but the EPSRC gave support to me and Steve Cully for work on research into the information access methods and requirements of engineering designers. Steve had done work in the electronic design catalogue. And at that time as well, my colleague at Rover put me in touch with a colleague of his called Laurie Burrow, who worked for a company which was GEC, became Converteam, looking at control systems. And another colleague introduced us to Florence Cellini at Airbus, who was responsible for their knowledge management. And together we built a team between Bath and Bristol, looking at knowledge and expert applications, advanced computing applications in engineering information and knowledge management, I would say. And such that by the end of the 90s, in about, I think 2001, I did this diagram reflecting back on the period from 87, that early work in automotive engineering expert systems, as we called it. In that work, we looked at feature-based design, advanced computing techniques, looked at hypermedia, which was emerging quite strongly in the late 80s. But we looked at the representation of incompleteness and uncertainty, which was a big issue in the failure of parametric automation to work in the company we were in. We looked at process modeling, and out of that came, first of all, 4 themes, with Steve looking at the designer's information requirements, with John Sims Williams looking at hypertext database systems and process modeling and automation, and risk and uncertainty in design. And out of those 4 themes came 4 further themes. The work in trying to understand the designer's information requirements and the work on hypertext database systems led in the late 90s to work with Airbus, looking at more general issues of information management and browsing in engineering. Work on process modeling and automation together with designers' information requirements led to a theme of work on information support for processes and through the life cycle. And risk and uncertainty in process automation led to work on response surfaces, also a sideline really on processing of materials. But I characterized my understanding of design then as design being the management of information and uncertainty. I got just and the questions I characterized also the questions that I was asking at that time. First of all, how can we use informatics to support design synthesis? And I was particularly concentrated on that adaptive invariant products, the automotive and aerospace industries. How can we use CAD to support the evaluation of properties? And very important, how can we document the process better and exploit the resulting records? Now, I think the lessons I learned there, first of all, serendipity again. If I hadn't been introduced to John, if Malcolm Sabin hadn't remembered me from a meeting, that would never have started. That whole line of work would never have got going. But the second lesson, probably the most important one to all fellow researchers, is the importance of enthusiastic industrial supporters and enthusiastic colleagues to work together with and learn from. Can't stress enough that if you can find enthusiastic colleagues and find enthusiastic industrial sponsors, they are gold dust. And what I would say is, in the early days of your research community, of your research work, say yes. Don't necessarily say it too often, but if people approach you with interesting problems, say yes, particularly if they have shared and complementary interests. But also, if you possibly can, try to get research funding which allows you to play and experiment. And finally, and I think this is a theme which will come through what I'll say, if you think you've got something interesting, don't be discouraged if you don't necessarily convince other people likewise. Don't give up. Looking back, I think there's a number of themes which I followed, which I thought was interesting, but felt discouraged when I couldn't get a response from people. And in retrospect, I should have kept going on them. So into the 2000s. And in 2002, I joined the University of Bath, and Bath at that time had what was known as an Innovative Manufacturing Research Centre funded by the EPSRC. And there was a long history of design and manufacturing research in the department there. And we worked together on 4 main themes within the IMRC there. 2 manufacturing themes in metrology and assembly systems and advanced manufacturing processes, and 2 design themes in constraint-based design and optimization, and in design information knowledge, which was centered around the work that Steve and I had been doing and with new colleagues in the research center there. And it was looking into the engineer's logbook, information push, and so on. In Bath, we got involved much more in a national community of researchers. We were encouraged by our research funders to work together in the community, and we led at Bath a program in knowledge and information management through life. And it was that program came out of 2 things. Again, industrial support. There was a man, Steve Shepherd, led a national group, the UK Council for Electronic Business, particularly in the aerospace industry, saying how can we use our computer systems over very long product lifetimes, 40, 50 years. We need to be able to revisit the design and the design rationale over that long period. And we were brought together with a group in construction led by Stuart Green at Reading, who had similar interests in facilities management in the construction industry. And this is just an illustration of what came out of this. In the KIM community, the researchers, we were asked to come up with our vision. And we talked then about how we could imagine in a few years' time having detection of a problem on a flight system, referring back to databases of service documentation, design documentation based around manufacturing and other features, lightweight representations used through the life of the artifact, but also novel methods of capturing the rationale at the design stage, design rationale capture from Cambridge, multimedia applied, automatically captured records from Heriot Watt, and the manufacturing features work came from Loughborough. So that in that we were working together as a team, but also with management researchers trying to understand the management issues at the time. Our work in particular then built on what I'd been doing in the 90s, looking at lightweight models and annotation of those lightweight models. Now, I now want to step back and talk about a thread which ran through that work, and you'll see in a minute why I raise it. Back at the end of the 80s, in that early work with John Sims Williams, in about 88, 89, we sat down and said, what, in our view, would an ideal engineering, information engineering, computing support system look like? Remember, this was before the World Wide Web. We said that we would want to be able to take the models and files that we were using and annotate them with hypertext and use collections of tags. We didn't call them tags, we called them attribute value pairs to in order to index the material. We wanted to be able to hyperlink between elements, but also have search-oriented hyperlinks which would search for related data, dynamic search. We built a system at the end of the 80s and the beginning of the 90s which did this, allows us to view different files, had all sorts of hypertext facilities within it, but also at that time we introduced a system whereby as we searched on attributes, we could have multiple dynamic filters. We'd select some key attributes first, and that would show the just those attributes that we could use in order to refine the search, and we could have repeated application of filters. We came to learn later that what we were doing then effectively was faceted search. Come on, 30 years, and if you go to many websites these days, they have faceted search as a standard feature. This is, for example, if you're wanting to look at car sales, the facets are that whether it's diesel or petrol, whether it's manual or automatic, number of seats, number of doors, and so on. We did that first in the early 90s, and then in web-based form we did it in about 2000. We tried to sell it to people that operated websites like the car sales website, and we couldn't interest them at all. This is in about 2001. And again, I was discouraged at that time, and 20 years later, it's a standard feature. Faceted browsing really is between the browsing of classification structures, which all manner of things have our directory structures on our disks, classification structures, and more sophisticated ontologies. Faceted browsing allowed us to, in effect, have multiple classification structures, each of which represented a different facet of information. And we saw that that might be particularly interested in the context of engineers looking at company data systems, where we couldn't establish a single classification, but we could establish many. We built a system at that time which also integrated faceted classification with automatic indexing. We tried to automatically index documents against that faceted scheme, and we integrated it in with keyword search so that you could go backwards and forwards between keyword search and faceted browsing. And we built it into a system which we tried to commercialize. We had a company for 3 years, and it built a classification system and a faceted browsing system. We had it used by Airbus, BP, Rolls-Royce, Babcock. But ultimately, we couldn't get continued funding to allow us to go beyond the 3-year time period. And at that time as well, all manner of other things were happening. We were running the big project, the Kim project, and to some extent we were distracted from trying to commercialize. And my lessons from that time are many. First of all, it takes a great deal of time to understand different communities. We only had 3 years with Kim to try and work with the management community. From that, I thought that mechanisms to maintain a continuous dialogue with other communities and to learn from them would be one of the most useful things we can do as a research community. In terms of personal lessons, try to develop a big picture view and where you fit. And if you have a real niche in that big picture, keep at it. Don't be distracted. But I guess the most important lesson is that managing success is very difficult. Once you start developing on multiple fronts, deciding where to prioritize, deciding, trying to get funding to maintain multiple streams, knowing when to drop a line of research can become very difficult. And I'm looking back, I'm not sure I did it very well, and I'm not sure. One of the key things I'd say is, whereas I say yes early in the career, later in the career, learn to say no and to prioritize. And I would say as well, if you do want to commercialize research outputs, it takes extraordinary tenacity and not some little luck to do so. So now on to the wider field. And again, some very important people in working life. And one of the most important for us in the British community was Ken Wallace, and I sort of felt right through the 90s it was and the 2000s it was Ken really watching over us and guiding us. And one of the things he did most in my working life was introduce me to Alex. Me and Steve joined Alex and Ken in ICED 2001, and that introduced me to the wider ICED community and eventually to the Design Society in 2005. But also right through the 90s, I'd worked with Bill Iron and colleagues in an organization called Sharing Experience in Engineering Design, looking at design teaching. And at the end of the 90s, we got together with the Institution of Engineering Designers, Libby Merrick, who was General Secretary of the IED, and we brought together 2 conferences to form the Engineering Product Design Education Conference, and that was an enormous pleasure working through the 2000s and onwards on that conference and on ISED. ISED 01 was working with the IMechE and WDK as it was, and in preparation for that, we looked at the 1999 proceedings, but we looked at the topics and keywords, and we found, some of you will have seen this, that there were 1,000 odd keywords and phrases used in the 1999 papers, and nearly 900 of them were only used once, and nearly 100 only twice, and the number of keywords which were used more than 3 or 4 times was absolutely tiny. We, because we were interested in information and knowledge management, we spent quite a lot of time looking at classification of topics for the conference and experimental use of automatic classification, and I'll come back to that in a minute. But we came up then with a suggestion for ISED 01 of this classification for topics, and we'll see in a minute that that more or less is the classification which we adopted later in that decade as the Design Society, with some changes. For each of those classification terms, we came up with a recommended set of keywords, and here's an example keyword list. And we had some success in getting them adopted, not as much as we hoped, but I mean, this is our 2001 keyword, and we see that there was still a lot of our suggestions were not used or were only used once, particularly in what we call current issues, globalization, sustainability and legislation. But in some areas, knowledge and information management, as you can imagine, that being our specialism, we got those about right. We had a very good usage of our keywords, and in others we got an improvement compared with what we'd had before. We also had this experimental use of automatic classification in preparing the proceedings. And this is a slide which I did in 2002, or a combination of 2 slides. We used a rule-based approach to that classification to try to see whether we could automatically allocate papers to sessions. We concluded at that time that it was possible. At least it was a very good starting point for those who were organising. At that time, I wrote the community is a little reluctant. It may be too early for an agreed classification, but we had quite a lot of comeback at that time that there needed to be a lot more discussion as to what the classification might be, but at least there was a basis for agreed categories and a recommended keyword list. In 2009, we introduced a consolidated topic list to be used for the ISED conferences, and this is looking back in 2015 as to how the numbers of papers in each of those consolidated areas had changed over the previous 3 conferences. And you can see that, I mean, design methods and tools, which was originally the heart of ISED, was down to less than 15% by 2013, whereas human behavior in design was growing quite strongly. Design theory and research methodology decline, product, service and system design, especially product services, growing quite strongly. Now, let me just ask, I've got probably about 5 more minutes. Is that okay, or would you prefer that I
go for it,
stop? Go for it. Okay, so I mentioned about facets, and my interest, the key thread, probably the biggest thread in running through my research has been this interest in facets, different aspects of topics and use of that for search and browse. And I, in 2011, applied it to the papers from 2009 conference. I said some facets of design research, not the classification of the topics, but in design, sometimes we study people working over very short periods of time, other times activities over many months. We study different life cycle phases. We study individuals to teams or communities. We study sometimes activities to large numbers of issues. We look at features up to complex systems, and so on. And I took the 2009 papers, some of you may remember this from 2011, and I categorized them by hand against these facets. And so this is the human behavior in design, showing that they concentrated a lot on individuals. They concentrated on single or small number of issues. They concentrated on the early life cycle stages, and they used particular design methodologies. The design organization and management, by contrast, if we look, concentrated much larger teams, on larger numbers of issues, on larger numbers of life cycle stages, and on and used rather different research methodology. And in fact, when we looked at all the different themes, we saw quite significant differences in the research methodology, and that in turn mapped onto the different facets that we used. So really my final point out of those last bits is find a bit of general advice. Find a community and stick with it. Find a conference that you enjoy, stick with it and contribute to it. Second point is we're a great community, but we don't have a lot of coherence, and that the keyword study showed that. Our diversity is a strength, but it's also a weakness. When we were looking at librarians, they talked about warrant. What was the basis for classification? And they said you can have classification which is done just because the users find it useful, or by study of the texts, that literary or user warrant. But you can also have classifications which have an underlying scientific basis. And really my question has been, what might be the underlying scientific warrant for the organisation of our subject? And finally, my recent obsession is we need to work on a big picture view of where design fits in society, and with respect to technology and engineering, natural and social sciences. And I think out of that will come real meaning for our community is how it can best contribute to the society. Thank you very much. And any comments or questions?
Thank you very much, Chris. This was really interesting and excellent. I suggest we do what we've done last time, is that if you want to pose questions to Chris, please put them in the comments, and I will summarize the questions and ask the questions so that we keep it on topics that are generally interesting. But maybe while everybody is going and thinking about their questions, could you comment a bit more about where you think design sits in the big picture? Because you ended on this note, but you didn't elaborate this.
Yeah, I mean, I'm very much an adherent to Herb Simon, everyone designs view. I mean, I think that in humankind's relationship with artifacts, we design things, we make things, we operate things, we repair things, we deal with things at the end of life, or we deal with the consequences of use of those things. So design for me is one of the absolutely central activities in humankind's relationship with the artificial world. And I think its importance is not yet understood fully by the rest of the community, but we haven't emphasized its importance enough, and we haven't dealt with its generality so much. I've seen recently, for example, work by lawyers learning from engineering designers, saying that lawyers design things. They design contracts for their clients, they design bills for their states, and so on, and that what lawyers do is not so different from what engineers do when you look at it. And I think more than that, we can also say that if you look at the challenges which face us, the challenges that we face just now are ones of redesigning our artificial world. We have an artificial world which is designed on the basis that we have ready availability of resources, especially fossil fuels, and designed on the basis that using those fossil fuels and other resources doesn't do too much harm. And we've learned that we don't have such ready availability, and we've learned that it does do harm. Therefore, we have to redesign everything. And what I see in a lot of the discussion by people concerned with those is that they are basically taking design stances, or and I think we have a great deal that we could say about that redesign of the artificial world.
Thank you very much, Chris. That's very interesting. One of the things that struck me listening to you is that many of the questions you've asked throughout your career, from the uncertainty, the information, the computer support, didn't go away in the meantime. And I was wondering whether you'd like to comment which of the ones you think are still relevant, and maybe what the questions are that we are going to have to address in the next 20 years.
Yeah, I mean, I think I examined a PhD recently, and it's involved quite a lot of qualitative research amongst companies, and they had a lot of the things which that researcher found were very much aligned with what we'd found 20 years ago. And I think an awful lot of the big questions that we had at that time, we've barely scratched on the answer. But at the same time, I also see that the computer, I showed that picture of the computer systems in the 90s, or in the 80s rather, by the end of the 80s. And an awful lot of the systems that we use now, their basis was established by the early 90s. And there's been a great deal of commercial interest spent on establishing that. If you look at the operating systems we have, the operating systems we use were, I mean, basically originated in the 80s, so on, and they were general purpose. They're not very well matched on the sort of uses we have. I mean, I think I'm rambling here, but the point I would make is that it would be worth re-looking at some of these fundamental questions and asking ourselves again to what extent we have addressed them, which questions still exist.
Thank you. Yeah, I think underneath this is what's rumbling in our questions here, and I think generally is we almost need to look at the same topics again that we have looked at before, and how we are getting funding for research that in a way has already been funded 20 years ago, but now we have got a higher level of maturity. So how do we persuade people to fund this higher TRL research?
Yeah.
Or we define our research as making fundamental contributions, but maybe to the art of applying something rather than the fundamental science or technology.
Yes, this is always the problem. There's this view that when people apply and they look at revisiting questions which have been supposedly revisited before, people say, we've done all that, why should we fund it again? And the fact that it wasn't solved it isn't usually a good enough answer. There's also, I mean, there's the case that very often changes in, for example, in computing performance can mean that techniques which didn't work very well 20 years ago now work very well. You look at all the sort of things that were done with neural nets once we were able to bring enormous computing power to bear on them. I'm not sure what the way forward with that is. I would certainly love to see the society have meetings where we systematically examine questions which have been important over the years and said, to what extent can we say, yes, we know that and move on? To what extent can we say, yes, that's still a real issue and we need to address it? And then try to influence the research agenda from the research funders in that respect. And I think industrial help can be very important there.
I think you're absolutely right. I think what you're picking up on, I think what the comments are picking up on is this issue of being both relevant to industry and to consolidate on what we have got already and make what we have better rather than making maybe more new things, just like with the design of products, with our own products, the tools and methods.
But what I will say, if you in 1990, where I thought CAD and computing would be by 2020, I would have imagined we would be much further on than we are. But actually, I mean, I wrote this textbook, second edition was 89. Much of it is still valid now, 30 years later. And in a lot of cases in design computing, the underpinnings haven't changed much in 30 years and maybe need re-examining. I mean, it might be interesting, you know, to re-examine all that was done in features in the 80s and 90s, for example.
Yes, I think we're all finding that it's very hard to do that consolidation, because I find that everything I've ever done is on certain extent still relevant and the questions are still open. And it sounds like some of your questions, that's the same thing. So how do we portray ourselves to industry as actually being competent and having something to contribute?
On the other, one of the other things is this gap. Industry wants to use day to day things which are sufficiently robust and stable enough and well supported enough that they can use them reliably. And this was the problem that we had with the trying to commercialize our system. People found it very, I think those who used it found what we were doing met their needs very well. But for example, a big British company wanted to use our software and they said, we'll buy it from you when you've got a blue chip client. And we said, well, can't get a, you know, if you bought it from us, you would be a blue chip client. And they said, well, no, we're not allowed to buy it from you because you haven't had a blue chip client. And there's often this sort of trough of despair, isn't it, between you know, the early stages and bringing something to the point that it's, yes, it's TRL 3 or 4, you use it, and bring it to 7 or 8 is very difficult to cross that gap.
But I think quite often in the higher TRLs, there are the fundamental questions that need to be addressed that I think we've always been pussyfooting around, like the role of representation in design or something, that are the real obstacles to the introduction later on. Yeah.
The other thing is finding, I mean, you can always get a representation which works for some particular context. I mean, I'd look at an awful lot of methods which supposedly were a new design for X method that worked automatically. And I look at those methods, and usually the first step was to spend a lot of time constructing a special representation on which the method works. And there was usually considerable expertise needed for the construction of that special representation. And you might as well have applied that expertise to the direct evaluation of the design in the first place. Methods which applied based on our relatively simple geometric models, or identifying feature-based representations which worked in multiple applications. Anyone can write a feature-based application which works for process planning, say. Others could write feature-based applications which work for engineering analysis or different analytical techniques, but a feature-based representation which worked in both was very difficult. In fact, they were non-commensurate usually.
But of course, now a lot of design research is moving to things that are no longer geometric and is looking at a much bigger picture of design being immaterial or being services or being processes. So how do you think it's playing out for that?
I think you still need need representations of those services, that you begin to see exactly the same problem in design for X, and making X judgments about services, or X judgments about networks, or X judgments about circuits, and so on. All of it comes down in the end, I believe, that you have characteristics describing the artifact, and you have to take representations of those characteristics and manipulate them in order to evaluate some properties, and that sort of fundamental step is everywhere. And likewise the other way. We've talked about automated design synthesis for many years, but again, it's a largely unsolved problem.
Yes, so I think you're absolutely right there. But of course, the challenge is that we, or many in our community, have come from a mechanical systems geometric perspective, and now we have to think about this in a much more interdisciplinary manner. Yeah. So I'm wondering whether you've got any thoughts on how we might be able to do that.
Yeah, I mean, I think the key word you use there is interdisciplinary. That we could have electronic representations and electronic evaluations. We can have mechanical representation, mechanical evaluations. The real issue I think we have today is that we have multiple disciplines, and the fundamental representation of characteristics in those multiple disciplines is incommensurate. That the electrical engineer uses a different representation from the mechanical, different in turn from the computer scientist, and so on. And that, I think, is an area, and cyber physical systems and so on, where there's enormous fundamental work to be done on representations, but also on the sort of multidisciplinary analysis and synthesis.
Yes, I see that very much as the battleground of the 2020s and 2030s. We had a very interesting question from Tetsuo, who was saying whether we can measure the progress of design research, or whether we're simply doomed to go around in circles.
Yes, I know. I was expected Tetsuo to ask a really insightful question like that. I mean, I think, again, just as it would be very useful for us as a community to go through and say every so often, what are the fundamental questions and how have we done it? To try and say, I mean, I'll just change the question a bit. What would a breakthrough look like in our discipline? What other areas breakthroughs are needed, and would we recognize one if it came? Have we had breakthroughs in the past, and what have those breakthroughs been? Would we see, for example, that in CAD the introduction of parametric CAD, such that, I mean, in my early days, I was writing programs to produce parametric geometry. Then along came parametric CAD, and we no longer needed to program it. It could be, in effect, done interactively by the designer, make a parametric model. I mean, looking back, I would see very often that the sort of results of that didn't work terribly well, and we might have been better to program it. But are there other areas where there have been breakdowns? I'd be very interested in anyone listening would be able to say, yes, I think X in design research has been a breakthrough. If there's any in the chat that could.
There isn't anything in the chat, and maybe that's a good point to end on, because I think we all need to reflect about this, whether we know what breakthroughs are, whether we would recognize breakthroughs. I think I often think of this as that design research is just about getting confused on a higher level.
Yes, I think it is.
Move from one confusion to the next, but you do clear up things in the process. Yeah. So I suggest we'll thank you very much for the talk at this point. It was really, really interesting and insightful. And thank you very much for listening. And if you have got any questions to Chris, I'm sure Chris is very happy to answer emails as well or engage in a dialogue with you. So thank you very much. And the next Design Society seminar is going to be in the middle of November, and we'll have Terry Knight from MIT talking about her research on shape grammars. So
thank you very much, everyone who's there. I look forward to hearing from anyone who would like to get in touch. And in the meantime, have a good afternoon, wherever you are.
And maybe not